Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Probability, before Andrei Nikolaevich Kolmogorov, resembled a ship without a rudder. It navigated the seas of chance, yielding results that often seemed reasonable, yet lacked the secure foundation of rigorous mathematics. Paradoxes abounded, and the absence of a universally accepted axiomatic system hindered progress. Girolamo Cardano, Pierre de Fermat, Blaise Pascal, Cauchy Huygens, and Jacob Bernoulli had all wrestled with aspects of probability, providing glimpses of its potential, but a comprehensive, logically sound framework remained elusive. These pioneers intuited the basic principles, yet their work lacked the formal rigor necessary to resolve inconsistencies and address increasingly complex problems. The central challenge lay in defining probability itself. Early attempts relied on intuitive notions of equally likely outcomes, a concept that proved inadequate when dealing with continuous variables or situations where symmetry was absent. This deficiency led to ambiguities and contradictions, impeding the development of a cohesive theory. One could calculate the odds of rolling a specific number on a fair die with relative ease, but determining the probability of a dart landing on a particular point on a dartboard presented a far greater challenge. The infinite possibilities demanded a more sophisticated approach. Kolmogorov's genius lay in recognizing that probability could be built upon the solid bedrock of measure theory, a branch of mathematics developed in the late 19th and early 20th centuries to rigorously define the size or measure of sets. Emile Borel's work on measure theory, particularly his contributions to understanding the real number line and his exploration of infinite sets, served as a direct inspiration for Kolmogorov's approach. Borel's insights into how to assign consistent measures to complex sets provided the mathematical tools Kolmogorov needed to formalize probability. In his seminal work, Foundations of the Theory of Probability, published in 1933, Kolmogorov presented his axiomatic system. This system, now universally accepted, defines probability as a measure on a sample space, a set representing all possible outcomes of a random experiment. The key axioms are remarkably simple, yet profoundly powerful. First, the probability of any event must be non-negative. This axiom reflects the intuitive idea that probabilities cannot be negative. They represent the likelihood of something happening, which can only be zero or positive. Mathematically, for any event in the sample space, the probability of R, denoted P of R, must be greater than or equal to 0. Second, the probability of the entire sample space must be equal to 1. This axiom formalizes the notion that something must happen. The probability of all possible outcomes occurring is certain, represented by the value 1. If omega represents the sample space, then P of omega equals 1. This axiom provides a normalization condition, ensuring that probabilities are scaled appropriately. Third, for any countable collection of mutually exclusive events, the probability of their union is equal to the sum of their individual probabilities. This axiom, known as countable additivity, is crucial for dealing with complex events that can be decomposed into simpler, non-overlapping events. If A1, A2, A3, and so on, are mutually exclusive events, meaning that the intersection of any two of them is empty, then the probability of the union of a sub I from I equals 1 to infinity is equal to the summation from I equals 1 to infinity of P of a sub I. This axiom allows us to calculate the probability of complex events by breaking them down into manageable parts. Consider a simple example: flipping a fair coin. The sample space consists of two outcomes, heads and tails. According to Kolmogorov's axioms, the probability of either heads or tails must be non-negative. The probability of getting either heads or tails must equal 1, representing certainty. If the coin is fair, we assign a probability of 1/2 to heads and 1/2 to tails. These probabilities satisfy all of Kolmogorov's axioms. The probability of getting heads is greater than or equal to 0. The probability of getting tails is greater than or equal to 0. And the probability of getting either heads or tails is 1/2 plus 1/2, which equals 1. While seemingly trivial, this example illustrates the power of Kolmogorov's axioms to provide a rigorous foundation for even the simplest probabilistic calculations. Kolmogorov's axiomatization had a transformative impact on the field of probability. It resolved existing paradoxes by providing a consistent and unambiguous framework for defining and manipulating probabilities. It enabled mathematicians to develop new and powerful tools for analyzing random phenomena. It paved the way for applications of probability in diverse fields, ranging from physics and engineering to finance and economics. Abraham Wald, for example, directly applied Kolmogorov's rigorous probability framework to develop statistical decision theory, revolutionizing how statisticians approach problems with uncertainty. The impact of Kolmogorov's work extends far beyond the realm of pure mathematics. His contributions have had a profound influence on our understanding of the world around us, shaping how we model and analyze complex systems. His axiomatization of probability provided a foundation for statistical inference, risk assessment, and decision-making under uncertainty. Without Kolmogorov's rigorous framework, many of the technological and scientific advancements of the 20th and 21st centuries would not have been possible. Probability theory, however, represents only one facet of Kolmogorov's multifaceted genius. His intellectual curiosity extended to a wide range of mathematical and scientific disciplines, each of which he enriched with his profound insights and innovative techniques. Subsequent investigations will explore his groundbreaking contributions to the understanding of turbulence, a problem that continues to challenge physicists and engineers. Further examination will reveal his pivotal role in the development of information theory, a field that underpins modern communication systems. Finally, we will delve into his pioneering work on algorithmic complexity, a concept that has revolutionized our understanding of randomness in computation. Kolmogorov's profound impact on mathematics extends far beyond the realm of probability. His insatiable intellectual curiosity led him to grapple with some of the most challenging problems in physics, including the perplexing phenomenon of turbulence. For centuries, scientists had struggled to develop a comprehensive theoretical description of turbulent flows characterized by their chaotic, seemingly random fluctuations in velocity and pressure. These flows defy simple analytical solutions, rendering traditional fluid dynamics approaches inadequate. The problem of turbulence is ubiquitous, appearing in diverse settings, from the flow of air over an airplane wing to the mixing of fluids in industrial processes and the movement of oceanic currents. Kolmogorov confronted this challenge head-on, initiating a new approach based on statistical methods. Rather than attempting to solve the governing Navier-Stokes equations directly, a task that remains largely intractable even today, he sought to characterize the statistical properties of turbulent flows. His groundbreaking work, primarily developed in the 1940s, provided a framework for understanding the energy cascade, a central concept in the physics of turbulence. The energy cascade describes the process by which energy is transferred from large-scale eddies to smaller and smaller eddies until it is ultimately dissipated as heat due to viscous friction. Imagine a large, swirling vortex in a river. This large eddy contains a significant amount of kinetic energy. The Kolmogorov theory posits that this large eddy will break down into smaller eddies, each possessing a fraction of the original energy. These smaller eddies, in turn, break down into still smaller ones, and so on, creating a hierarchy that is spanning a wide range of scales. At each stage of this cascade, energy is transferred from larger to smaller scales, with some energy lost to viscous dissipation. This cascade continues until the eddies reach a size scale where viscosity becomes dominant. These smallest scales are known as the Kolmogorov scales, and they define the limit at which turbulent energy is converted into heat. The Kolmogorov length scale, denoted by eta, is given by the square root of the kinematic viscosity cubed divided by the average energy dissipation rate. The Kolmogorov velocity scale is given by the square root of the product of the kinematic viscosity and the average energy dissipation rate. Finally, the Kolmogorov time scale is given by the square root of the kinematic viscosity divided by the average energy dissipation rate. These scales are fundamental parameters characterizing the behavior of turbulence at its smallest, most dissipative levels. One of the most significant results of Kolmogorov's statistical theory is the two-thirds law, which describes the relationship between the energy spectrum and the Wade number in the inertial subrange. The inertial subrange is the range of scales where energy is transferred conservatively from larger to smaller eddies without significant dissipation. The two-thirds law states that the energy spectrum, which represents the distribution of energy across different scales, is proportional to the Wade number raised to the power of negative 5/3. Mathematically, this can be expressed as E of k is proportional to k to the power of negative 5/3, where E of k is the energy spectrum and k is the Wade number. This law has been experimentally verified in numerous turbulent flows and provides a powerful tool for analyzing and predicting turbulent behavior. Consider, for example, atmospheric turbulence. Aircraft engineers use the two-thirds law to estimate the intensity of atmospheric turbulence at different altitudes. This information is critical for designing aircraft that can withstand the stresses imposed by turbulent airflows and for developing flight control systems that can compensate for these disturbances. By measuring the energy spectrum of atmospheric turbulence, engineers can predict the loads that an aircraft will experience during flight and ensure that the aircraft is structurally sound. A key element of Kolmogorov's theory is the universality hypothesis. This hypothesis asserts that the statistical properties of turbulence at small scales are independent of the specific details of the large-scale flow. In other words, the energy cascade and the Kolmogorov scales are determined primarily by the average energy dissipation rate and the kinematic viscosity, regardless of how the turbulence was initially generated. This universality allows scientists and engineers to apply Kolmogorov's theory to a wide range of turbulent flows, from those found in industrial applications to those occurring in natural environments. While Kolmogorov's original theory provided a groundbreaking framework for understanding turbulence, it was not without its limitations. His initial formulation assumed that the energy dissipation rate was statistically uniform in space. Subsequent research, particularly by Soviet scientists A.M. Abarakov and A. Gaglam, revealed that the energy dissipation rate itself exhibits significant fluctuations, leading to deviations from the two-thirds law. These fluctuations, known as intermittency, arise from the fact that turbulent energy is concentrated in localized regions of high vorticity. Refinements to Kolmogorov's theory have addressed the issue of intermittency by incorporating statistical models of the energy dissipation rate. These models, often based on log normal or Beer distributions, account for the non-uniformity of energy dissipation and provide more accurate predictions of the energy spectrum in turbulent flows. Uriel Frisch, for instance, developed multifractal models to characterize the scaling properties of turbulence, building upon the foundations laid by Kolmogorov and his successors. These advancements demonstrate the enduring legacy of Kolmogorov's work, which continues to inspire and guide research in the field of turbulence. The work of Lars Onsager regarding energy conservation in ideal fluids, specifically his conjecture about anomalous dissipation, influenced Kolmogorov's thinking about the energy cascade. Kolmogorov's statistical theory, in turn, profoundly impacted the work of researchers like William K. George, who developed advanced models for turbulent shear flows based on Kolmogorov's ideas. Kolmogorov's insights into turbulence, while representing a significant contribution to fluid dynamics, constitute merely one aspect of his diverse intellectual pursuits. His profound impact extends into the realm of information theory, where he independently formulated concepts pivotal to the digital age. The subsequent part will explore his groundbreaking work in quantifying information, revealing its profound implications for communication, computation, and our understanding of randomness itself. Kolmogorov's insights into turbulence, while representing a significant contribution to fluid dynamics, constitute merely one aspect of his diverse intellectual pursuits. His profound impact extends into the realm of information theory, where he independently formulated concepts pivotal to the digital age. The subsequent exploration will reveal his groundbreaking work in quantifying information, examining its profound implications for communication, computation, and our understanding of randomness itself. Prior to the mid-20th century, the concept of information, while intuitively understood, lacked a rigorous mathematical definition. Engineers and scientists grappled with the challenge of quantifying the amount of information contained within a message, a signal, or a data set. How many bits are required to represent a photograph? How efficiently can speech be transmitted over a telephone line? These practical questions demanded a theoretical framework for measuring information itself. Claude Shannon at Bell Labs provided a revolutionary answer. Simultaneously and independently, Andrei Kolmogorov was developing a similar framework in the Soviet Union. Kolmogorov's work in information theory, conducted largely independently of Shannon's, centered on the fundamental problem of quantifying information content. He sought a measure that would capture the intuitive notion that some events or data sets convey more information than others. A highly predictable event, for instance, carries little information, whereas a surprising or unexpected event carries a great deal. This challenge demanded a mathematically precise definition of surprise or unexpectedness. Kolmogorov's approach led him to independently derive the entropy function, often denoted as h of x, where x represents a random variable. This function serves as a measure of the average uncertainty associated with a random variable, or, equivalently, the average amount of information gained by observing its value. The entropy function is defined as the summation over all possible values x of p of x multiplied by the logarithm, base 2, of 1 divided by p of x, where p of x is the probability of observing the value x. Expressed concisely, h of x equals the summation of p of x times the logarithm, base 2, of 1 over p of x. This formulation elegantly captures the inverse relationship between probability and information content. The lower the probability of an event, the higher its information content. While both Kolmogorov and Shannon arrived at the same fundamental entropy function, their approaches and motivations differed in subtle yet significant ways. Shannon, working within the context of communication systems, focused on the efficient transmission of information across noisy channels. His primary concern was maximizing the rate at which information could be reliably transmitted. Kolmogorov, on the other hand, approached the problem from a more foundational perspective, seeking a universal measure of randomness and information content applicable across various domains, including probability theory, statistics, and dynamical systems. Shannon's work was immediately embraced by the engineering community, while Kolmogorov's contributions initially resonated more strongly with the theoretical mathematics and physics. A key area where Kolmogorov made substantial contributions was rate distortion theory. This branch of information theory addresses the problem of compressing data while allowing for a certain level of distortion or information loss. In many practical applications, perfect reconstruction of the original data is unnecessary or even undesirable. For example, in image or audio compression, a small amount of distortion may be imperceptible to the human eye or ear, allowing for significant reductions in file size. Kolmogorov developed mathematical tools for quantifying the trade-off between compression rate and distortion, providing a theoretical foundation for designing efficient lossy compression algorithms. To illustrate the concept of entropy, consider a simple example. Suppose we have a discrete random variable x that can take on two values 0 and 1. Let the probability of x equaling 0 be p, and therefore the probability of x equaling 1 is 1 minus p. The entropy of x is then given by h of x equals p times the logarithm, base 2, of 1 over p, plus 1 minus p times the logarithm, base 2, of 1 over 1 minus p. If p equals 0.5, meaning that the two values are equally likely, then the entropy is maximized at 1 bit. This corresponds to the maximum uncertainty, as we have no prior knowledge to favor one value over the other. Conversely, if p equals 0 or p equals 1, then the entropy is 0, indicating that there is no uncertainty, as the value of x is completely predictable. The entropy function, as defined by both Shannon and Kolmogorov, has found widespread applications in various fields. In data compression, it provides a theoretical limit on the achievable compression rate for a given data source. Compression algorithms, such as Huffman coding and arithmetic coding, aim to approach this limit by assigning shorter codes to more frequent symbols and longer codes to less frequent symbols. In cryptography, entropy is used to measure the randomness of encryption keys and to assess the security of cryptographic systems. A high entropy key is more difficult to guess or crack than a low entropy key. Beyond entropy itself, Kolmogorov also contributed to the concept of epsilon entropy, which considers the minimal number of bits needed to describe a set of objects with a given level of accuracy, epsilon. This concept has applications in approximation theory and numerical analysis, where it is often necessary to approximate complex functions or data sets with simpler representations. While Kolmogorov's work in information theory shares fundamental similarities with Shannon's, its emphasis on universality and its connections to other areas of mathematics and physics had a lasting impact on the field. His independent derivation of the entropy function solidified its central role in quantifying information and randomness, laying the groundwork for numerous subsequent developments in communication, computation, and our understanding of complex systems. The work of Norbert Wiener on cybernetics, with its emphasis on information and control, provided a parallel intellectual environment that fostered the development of information theory. Kolmogorov's contributions, in turn, influenced the work of researchers like Gregory Chaitin, who explored the connection between information theory and computability. Kolmogorov's pioneering work in information theory, though representing a cornerstone of the digital age, constitutes merely one facet of his multifaceted intellectual contributions. The subsequent exploration will delve into his groundbreaking work in algorithmic complexity theory, revealing its profound implications for defining randomness and understanding the limits of computation. Kolmogorov's pioneering work in information theory, though representing a cornerstone of the digital age, constitutes merely one facet of his multifaceted intellectual contributions. The subsequent exploration will delve into his groundbreaking work in algorithmic complexity theory, revealing its profound implications for defining randomness and understanding the limits of computation. The seeds of information theory, carefully cultivated by Kolmogorov, took root and blossomed, yielding not only new understandings of communication, but also inspiring researchers such as Gregory Chaitin and explorations of the deep connections between information and the very nature of computation. Kolmogorov's signal contributions to information theory, while foundational to our contemporary digital landscape, form but one vibrant thread in the rich tapestry of his intellectual achievements. We now turn our attention to his revolutionary work in algorithmic complexity theory, a field he essentially founded, and examine its profound implications for objectively defining randomness and eliminating the inherent limits of what can be computed. At the heart of algorithmic complexity theory lies a deceptively simple question: what does it truly mean for something to be random? The intuitive understanding of randomness often relies on subjective impressions or statistical tests, none of which provide a truly definitive answer. Consider, for instance, a sequence of coin flips. While a sequence of alternating heads and tails might appear suspiciously ordered and therefore non-random, any specific sequence of a reasonable length even one that appears random, has an equal probability of occurring. This inherent paradox highlights the difficulty in pinning down an objective definition of randomness. Kolmogorov proposed a radical departure from traditional approaches. He suggested that the complexity of an object, be it a sequence of numbers, a piece of music, or even a photograph, could be objectively quantified by the length of the shortest computer program capable of generating that object. This measure, now known as Kolmogorov complexity, descriptive complexity, or program size complexity, provides a powerful and elegant way to distinguish between truly random objects and those that merely appear so. To understand this concept more fully, imagine two sequences of 1,000 binary digits, zeros and ones. The first sequence consists of alternating zeros and ones 010101010. The second sequence is generated by repeatedly flipping a fair coin 1,000 times. Intuitively, the first sequence feels very ordered, while the second feels random. According to Kolmogorov's definition, the first sequence has low complexity. A short computer program, perhaps only a few lines of code, could easily generate this sequence by instructing the computer to repeatedly print 01. The second sequence, however, is likely to have high Kolmogorov complexity. Since it was generated randomly, the shortest program to reproduce it would likely be the sequence itself, stored verbatim in the program's memory. A crucial element in Kolmogorov's definition is the concept of a universal Turing machine. A Turing machine, conceived by Alan Turing, is a theoretical model of computation that can simulate any computer algorithm. A universal Turing machine is a special kind of Turing machine that can simulate any other Turing machine. It takes as input a description of another Turing machine and the input to that machine, and then simulates the behavior of that machine on that input. The existence of universal Turing machines is fundamental to the notion of Kolmogorov complexity because it provides a common standard for measuring the length of computer programs. The Kolmogorov complexity of an object is defined relative to a specific universal Turing machine. This raises an important question: does the choice of universal Turing machine significantly affect the Kolmogorov complexity of an object? The answer, reassuringly, is no. The invariance theorem, a cornerstone of Kolmogorov complexity theory, states that the Kolmogorov complexity of an object is independent of the choice of universal Turing machine up to an additive constant. This means that if we use two different universal Turing machines to measure the complexity of the same object, the resulting complexities will differ by at most a fixed amount, regardless of the object's complexity. The invariance theorem ensures that Kolmogorov complexity is a robust and objective measure, immune to the idiosyncrasies of particular computational models. Consider the implications of Kolmogorov complexity. A string of purely random bits possesses a high Kolmogorov complexity, approaching the length of the string itself. In contrast, a highly ordered structure, such as a repeating pattern or a simple geometric shape, exhibits a low Kolmogorov complexity corresponding to the concise program needed to describe its construction. A visual example might be a perfectly rendered Mandelbrot set. While appearing infinitely complex at various magnifications, the Mandelbrot set is generated by a very short iterative equation. This contrast is a tangible demonstration of Kolmogorov's measure. Despite its theoretical elegance, Kolmogorov complexity suffers from a significant limitation: it is uncomputable. This means that there exists no general algorithm that can take an arbitrary object as input and output its Kolmogorov complexity. This uncomputability stems from the halting problem, a fundamental result in computer science, which demonstrates that it is impossible to determine, in general, whether a given computer program will eventually halt or run forever. The uncomputability of Kolmogorov complexity does not diminish its theoretical importance, but it does mean that we cannot, in practice, determine the exact complexity of most objects. We can, however, obtain upper bounds on Kolmogorov complexity by finding short programs that generate the object. Kolmogorov's work also reveals a profound connection between algorithmic complexity and Shannon's information theory. Shannon's information theory quantifies the amount of information contained in a message or a random variable. Kolmogorov complexity can be seen as a refinement of Shannon's notion of information, taking into account the computational resources required to generate the information. While Shannon's theory focuses on the statistical properties of information sources, Kolmogorov complexity delves into the algorithmic structure of individual objects. This connection provides a deeper understanding of the relationship between randomness, information, and computation. The exploration of algorithmic complexity did not end with Kolmogorov. Building upon his foundational work, researchers such as Gregory Chaitin and Ray Solomonov made significant contributions to the field. Chaitin, in particular, explored the concept of omega, also known as Chaitin's constant, which represents the probability that a randomly constructed computer program will halt. Omega is a real number that is both random and uncomputable, embodying the inherent limits of computation. Solomonov, independently of Kolmogorov, developed a similar theory of algorithmic probability, which provides a framework for inductive inference and prediction. Kolmogorov complexity, despite its inherent limitations, provides a powerful framework for understanding randomness, information, and computation. It offers an objective measure of complexity that is independent of subjective impressions or statistical tests. It reveals deep connections between information theory and computer science. It continues to inspire research in diverse areas, including artificial intelligence, machine learning, and cryptography. His insights offer a profound perspective on the nature of information and the limits of knowledge. The consideration of Kolmogorov's algorithmic complexity theory reveals a facet of his intellectual brilliance, one that grapples directly with the fundamental limits of computation and the very definition of randomness itself. The subsequent discussion will turn to a seemingly different area of endeavor, Kolmogorov's profound impact on mathematics, education, and reveal the same commitment to fundamental principles and insightful problem solving that characterized all his work. Kolmogorov's algorithmic complexity theory, with its inherent limitations, provides a powerful framework for understanding randomness, information, and computation. It offers an objective measure of complexity independent of subjective impressions or statistical tests. It reveals deep connections between information theory and computer science. It continues to inspire research in diverse areas, including artificial intelligence, machine learning, and cryptography. His insights offer a profound perspective on the nature of information and the limits of knowledge. The consideration of Kolmogorov's algorithmic complexity theory reveals a facet of his intellectual brilliance, one that grapples directly with the fundamental limits of computation and the very definition of randomness itself. Attention now turns to a seemingly different area of endeavor, Kolmogorov's profound impact on mathematics education, revealing the same commitment to fundamental principles and insightful problem solving that characterized all his work. Kolmogorov dedicated a significant portion of his career to the improvement of mathematics education within the Soviet Union. He believed that mathematical understanding should be cultivated through intuition and active problem solving rather than through rote memorization of formulas and procedures. This philosophy underpinned his extensive efforts to reform the Soviet mathematics curriculum, particularly at the secondary school level. One key aspect of Kolmogorov's educational reforms was the introduction of abstract concepts, such as set theory and mathematical logic, into the high school curriculum. This was a bold move at the time, as these topics were typically reserved for university-level study. Kolmogorov argued that introducing these fundamental ideas early would provide students with a more solid foundation for advanced mathematical thinking. He saw set theory, for instance, as a unifying language that could clarify and simplify many areas of mathematics. He championed its inclusion to promote a deeper, more conceptual understanding. This approach was a departure from the traditional emphasis on computational skills and specific problem-solving techniques. Kolmogorov's influence on the Soviet mathematics curriculum can be seen in the widely used textbooks he co-authored. One particularly influential work was his probability theory textbook for secondary students. This book presented probability in a rigorous yet accessible manner, emphasizing the underlying mathematical principles and their applications to real-world problems. The textbook reflected Kolmogorov's belief that students should be actively engaged in the learning process, encouraging them to explore mathematical ideas through experimentation and discovery. The book emphasized the importance of understanding the concepts rather than simply memorizing formulas. Beyond curriculum reform and textbook writing, Kolmogorov was deeply involved in promoting mathematical creativity and independent thinking among students. He actively participated in mathematical olympiads, competitions designed to challenge and inspire talented students. He also mentored young mathematicians, encouraging them to pursue their own research interests and develop their problem-solving abilities. Kolmogorov believed that the most important goal of mathematics education was to foster a love of mathematics and to cultivate the ability to think critically and creatively. His educational philosophy had demonstrable effects on the following generation of Soviet mathematicians. Many of his students and collaborators went on to make significant contributions to various fields of mathematics and science. His influence can be seen in the work of mathematicians such as Vladimir Arnold, who made fundamental contributions to dynamical systems theory. Arnold himself emphasized the importance of geometric intuition and visual thinking in mathematics, echoing Kolmogorov's emphasis on intuitive understanding. Another mathematician influenced by Kolmogorov was Yakov Sinai, renowned for his work on ergodic theory and dynamical systems. Sinai's research reflects Kolmogorov's deep interest in the interplay between randomness and determinism. Kolmogorov's work in education built upon the earlier pedagogical theories of mathematicians like Georgy Pauler, who emphasized problem-solving heuristics and the art of mathematical discovery. Pauler's book, How to Solve It, had a significant influence on Kolmogorov's approach to mathematics education, reinforcing his belief in the importance of intuition in creative problem-solving. Kolmogorov, in turn, influenced later educational reformers who sought to move away from rote learning and promote more active and engaging approaches to mathematics education. The breadth and depth of Kolmogorov's contributions across diverse fields of mathematics are truly remarkable, from his early work on trigonometric series and set theory to his groundbreaking contributions to probability theory, turbulence, dynamical systems, information theory, and algorithmic complexity. Kolmogorov left an indelible mark on 20th century mathematics. His work is characterized by deep commitment to rigor, a remarkable ability to bridge the gap between theory and application, and a relentless pursuit of fundamental questions. One unifying theme underlying Kolmogorov's work is his emphasis on the power of abstraction. He believed that mathematics should strive to identify the essential structures and patterns that underlie seemingly disparate phenomena. This approach is evident in his axiomatic formulation of probability theory, which provided a rigorous and abstract framework for studying randomness. It is also apparent in his work on algorithmic complexity, which sought to define the notion of randomness in a mathematically precise way. Another unifying theme is Kolmogorov's deep interest in the interplay between order and chaos. He explored this theme in his work on dynamical systems, where he studied the long-term behavior of complex systems. He also investigated the relationship between randomness and determinism in his work on turbulence and information theory. Kolmogorov believed that understanding the interplay between order and chaos was essential for understanding the world around us. The enduring legacy of Kolmogorov's work can be seen in its continued relevance in modern mathematics and science. His axiomatic formulation of probability theory remains the foundation for all modern work in probability and statistics. His contributions to turbulence theory continue to inspire research in fluid dynamics and related fields. His work on dynamical systems has had a profound impact on fields ranging from physics to economics. His insights into information theory and algorithmic complexity continue to shape our understanding of computation and information. Kolmogorov possessed a unique ability to combine deep theoretical insights with a practical problem-solving approach. He was a master of both abstract mathematical reasoning and concrete applications. This combination of skills made him an exceptionally versatile and influential mathematician. He approached every problem with a fresh perspective, seeking to uncover the underlying principles and structures that govern its behavior. This approach allowed him to make groundbreaking contributions to a wide range of fields, leaving a lasting impact on the course of mathematics and science. Kolmogorov stands as a towering figure whose work continues to inspire and challenge mathematicians and scientists around the world. His intellectual curiosity, his commitment to rigor, and his profound insights into the nature of randomness and complexity have cemented his place as one of the most influential mathematicians of the 20th century.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.